Alright, and report number FRA ORD draft evaluation of locomotive cab airflow meters for train air brake leakage monitoring DRL Quebec SM Kiger Batali Columbus Division 505 King Avenue Columbus Ohio 43201. R&R Research Incorporated 1373 Grandview Avenue Columbus Ohio 43212. Department of Transportation and United States of America, April 28th, 1989. Final report, technical tax number 4, contract number DTFR 53864 and 6. Document is available to the U.S. public through the National Technical Information Service, Springfield, Virginia, 22161. Prepared for U.S. Department of Transportation, Federal Railroad Administration, Washington, D.C. 20590. Notice the United States government does not endorse products manufacturers, trade manufacturers' names appears herein solely because they are considered essential to the object of this report. Notice this document is disseminated under the sponsorship of the Department of Transportation in the interest of the information exchange. The United States government assumes no liability for its contents or use thereof. Then it shows the technical report documentation page. Evaluation of locomotive cab airflow meters for train brake leakage commenced April 28, 2089. Federal Railroad Administration, Office of Research Division, Development. Alright, railroad for abstract. Railroad freight train brake system must be qualified safety operation meeting with 3 brake pipe test criteria. 1, a minimum pressure of 60 psi gauge to the rear of the train. 2, a maximum pressure gradient of 15 psi over the length of the train, and 3, the maximum leakage of 5 psi per minute after applying the brakes. With the advent of the pressure maintaining feature for the brake control valve 26L equipment or the equivalent, brake pipe leakage limit becomes a little critical measure of the controllability of the train brake system. By the addition of airflow meter and indicator of the locomotive control stand instrumentation and alternate brake system leakage test, the airflow method was possible. This method provides advantages in the qualifying train brakes for operation extreme cold weather as well as means for over-road monitoring brake system leakage. This report includes extensive reviews of the technical literature, past experiences with the airflow method, engineering analysis. Airflow meters was conducted in the context of the airflow method. The analysis covers the accuracy and reliability of the meters, required airflow method calibration procedures, and the accuracy of the calibration devices themselves. Keywords: airflow method, train air brakes, airflow meters, airflow indicators, brake system test. Metric conversion chart. Alright, table of contents. Executive summary. 1. Introduction. 2. Technical literature review with federal regulations, train brake system operation, air brake system flow, and leakage response relationships, airflow test method, recent brake system studies. 3. Evaluation airflow method, airflow measurement operation experience with the airflow method, airflow meter calibration, engineering evaluation, airflow method, airflow relationship with aero analysis, airflow meter accuracy requirements, airflow meter reliability. References in Appendix A, AAR specification M980. List of figures. We'll view those. Her executive summary: the railroad freight train brake system must be qualified and safe for the operation, meeting with 3 brake pipe test criteria: minimum pressure of 60 psi gauge to the rear of the train, maximum pressure gradient of 15 psi over the length of the train, a maximum leakage 5 psi per minute after applying the brakes, with the advent of the pressure maintaining feature brake control device of the 26L equipment or equivalent. Brake pipe leakage limited because of the less critical of the measured controllability of the train brake system by the addition of the airflow meter indicator, locomotive control instrumentation, alternative brake system leakage test. Airflow method was possible for the method to provide advantage of the qualifying train brakes operation extreme cold weather as well as the means of over-road monitoring braking system. Based on the result of the laboratory tests on full-scale train brake systems in the early 1970s, Canadian railroads initiated field tests for the airflow method in 1974. Since December 1978, the airflow method has been used system-wide for the Canadian railways. This method officially sanctioned by the Canadian Transport Commission on April 30th, 1984, as a substitute for the brake pipe leakage rate test when controlling unit of the locomotive pressure maintaining brake control valve. Over the past several years, certain railroads of the United States have gained experience with the airflow method under the waiver of the FRA. Extensive experience both of the Canadian and U.S. railroads uncovering no train safety-related problems with the airflow method. Use of the airflow method has allowed the operation of longer trains, estimated from 10 to 15 additional cars into the cold weather, and the use of the airflow indicators in over-the-road operation, allowing continuous monitoring of the train brake system conditions. This use has received favorable commentary from the train crews. This report included the extensive review of the technical literature, past experience with the airflow method, engineering analysis of airflow meters conducted with the contact with the airflow method, with the analysis coverage of the accuracy and reliability with the meter required with the airflow method, calibration procedure for the accuracy of the calibration devices themselves. Currently used airflow meters are differential pressure gauges measuring the pressure drop of the 19 over 64 inches of the metering orifice of the flow measure, therefore nonlinear, varying as the square root of the pressure drop with the result of a large change of the airflow per gauge phase division low end scale. End of the scale, relatively small change of flow per division with a high end scale. The airflow meter is calibrated at 60 standard cubic feet per minute, which is established by the industry as a safe leakage flow limit to the calibration points for the mid-range for the meter for the minimize the effects of the nonlinear behavior. With view of the differential pressure gauge of the measure airflow with the airflow indicator reading accuracy is dependent with addition of the basic gauge accuracy within three factors. 1, the main reserve air pressure. 2, the main reserve air temperature. 3, the atmospheric barometric pressure due to the altitude. The pressure is set with the second of the main reservoir pressure over 10 psi range, which produced with the 2 cubic feet per minute. Changed in the reading of the nominal 60 square cubic feet per minute. Airflow arranged for the air temperature curve with a similar change with the flow reading with the actual flow rate is 60 square cubic feet per minute, which, since both of the measuring orifices of the calibration devices produce the similar change with the calibration reading of comparable leakage reading would remain the same with the temperature in itself of the air, but the combination of the air produce with the probable RMS air range of 2.75 cubic feet a minute, which exceeds the required and plus or minus 2.75 cubic feet a minute, with exceeded the required accuracy limits with the AAR specification M980 or airflow indicators. The Association of American Railroad calibration procedure for the airflow method, the type of the airflow indicators are RP402, means type of the temperature independence of the metering device requiring calibration devices you provided with 60 cubic feet a minute or 0.0765 pounds a second. The temperature no greater than 20 degrees Fahrenheit with the requirement minimizes the airflow reading as the low temperature with the actual leakage is of the greater significance. Control currently both leakage rate tests and airflow test methods rely on the standard air pressure gauge qualified for the train brake system for service for the need for the differential pressure gauge for the airflow indicator for the industry chosen for the rugged, reliable device for the long history of the locomotive so that the airflow indicator can be maintained on the same 92-day cycle as other air pressure gauges in the locomotive cab. Alright, final report. Technical task number 4, contract number ZTFR5386C, typical 406, evaluation locomotive airflow, train brakes, and 1 introduction. Alright, the Federal Railroad Administration has been petitioned for the Shovel Railroad to modify the Title 49 CFR 232 with the permit use of the cab airflow meter for the conduct internal and initial terminal and road train air brake leakage test. Current rules require that the train brakes to meet 3 criteria for the initial terminal at the point of the terminal where one of the more cars are added to the train. Minimum brake pressure of 60 psi for the last curve of the train, a maximum gradient of 15 psi over the length of the train, maximum leakage of 5 psi measured in 30 to 60 seconds of the after the exhaust from a 15 psi surface production, brake signal with the brake valve pressure maintaining function off. The leakage rate test of the measure controllability with the train brake system, assuming the system is not equipped with the pressure from the maintaining valve, with widespread use of the pressure maintaining valves on the modern locomotives, plus addition of the airflow meters may make the increased leakage rates practical without adverse effects of the on operations. Safety. This could cover the increase of the railroad productivity, the colder climates with the leakage rate, with the probable wind, with the flow rate, test for the wooded value, with the system leakage, with the not just for the brake pipe leakage, and in addition, even the onboard flow meter could provide with the continue with the mining with the brake system function for doing during over-the-road operation conditions for the railroad have conducted tests with the brake pipe airflow measure for the establishing 60 square cubic feet per minute. Leakage flow rate limit for these railroads over the 10 years operational experience with the flow of the rev and the pressure rate leakage limit for the use of the airflow meters can particularly beneficial during the cold weather when brake pipe leakage is at a maximum use of 60 square feet for a minimum minute as a criteria for the satisfactory brake system leakage permits for the railroads to operate longer trains during cold weather. Several U.S. railroads include Burlington Northern and have obtained authority to test UVD air use of flow meters. 2. Technical literature review. 2.1 Federal regulations. Current Federal Record Administration regulations propose train air brake discs contained in Part 232 Railroad Power Brakes without drawbars of Title 49 CFR Chapter 2 1 October 1st, 1987 edition, reference 1, and in the section 232.12, usual terminal road train air brake test of the regulations state that the inspection will be determined that 1. The brake pipe leakage does not exceed 5 pounds per minute. D. 1. After the air brake system freight train is charged within 15 pounds of the setting feed valve on the locomotive not less than 60 pounds with the indicator of the air correct gauge for the rear of the end of the train empowerment suit with the signal L apply brakes for the test. 15-pound brake pipe surface reduction must be made with the automatic brake operation of the brake of the valve with the lap of the number of the pounds of the brake pipe leakage per minute noted as indicated with the brake pipe gauge. D3, when the locomotive uses the hull of the train provided with the means of maintaining brake pipe pressure at a constant level during surface application for the train brakes, this is the feature that must be cut out during the train air brake test. E. The brake pipe leakage must not exceed 5 pounds per minute. In section 232.13 of the road train intermediate terminal train air brake test, leakage test is similarly described. D1. If at the point other than the terminal, one or more of the cars ahead of the train after the train brake system is drawn with not less than 60 pounds, with the indicator of the gauge for the device for the rear of the train with the brake test, if it must be made with the determine the brake pipe leakage does not exceed 5 pounds per minute, is indicated by the brake pipe gauge after the 20-pound brake pipe reduction. The additional 5-pound reduction of the brake pipe pressure of the 20 instead of 15 makes an intermediate point leakage test with a little less severe. Allows combining with the leakage test with the test for the train brakes at the rear of the wheel apply. In a related regulation, section 232.19, end of the train device accuracy for the pressure rating measuring device is addressed as B1, capable of measuring the rear car brake pipe pressure with the accuracy of 3 plus or minus 3 psi gauge brake pipe pressure variations on plus or minus psi gauge resolution. The regulation also defines the operation environmental of the rear unit and D and on the front unit F and the temperature and humidity, altitude, shock, and vibration. 2.2 Train air brake system operation. Train air brake system operation test procedure that described the definition 1971 technical paper Blaine with the Hangel reference to with the paper the description of the basic elements of the air brake system as well with the effect of the brake operation test procedure on the train. Basic car mounted unit of the air brake system consists of the brake pipe control valve with auxiliary emergency air reservoir, brake cylinder, and mechanical linkage of the brake shoe. For these elements shown in figure 2.1 with the brake pipe of the train common with the air pressure source with the pressure communication line with the train brake system travel with the locomotive mounted with the air compressor for the nominal brake pipe pressure setting, usually 75 to 90 psi gauge locomotive with the control valve. Depending on local operation procedure for the brake pipe pressure will droop with a distance over the rear of the train with a gradient due to flow induced pressure loss depending on localized leakage with the house, coupling, and fittings, etc. Operation train brakes initiated by the reducing the brake pipe pressure for the blowing off the air with the automatic brake valve of the locomotive serve the reduction consists of the brake pipe with the pressure reduction of 5 to 25 psi gauge. Full serve the reduction is one of the efficient with the valve of the pressure equalization between the brake cylinder and auxiliary reservoir. Individual control valve with sequentially sense of the pressure drop of the divert of the air for the auxiliary reservoir to the brake cylinder building up the cylinder pressure brake force on the wheel of the valve and sensitive to the brake pipe pressure drop of the 20 psi drop in more than 1.4 seconds can substitute with a normal surface application of the brakes, while with a drop of 20 psi in less than 1.2 seconds will induce emergency brake application. Nominally quick surface brake application of the ABD and ABDW valves propagate the torque of the rear over the 400 and 600 feet per second, while an emergency application will propagate 90 to 950 feet per second. Typical brake action times were cited in the paper for the single car full surface reduction brake pipe with the pressure of the 80 to 55 psi gauge will bring the brake cylinder pressure from 0 to 50 psi gauge in about 10 seconds, 57 psi gauge in 15 to 16 seconds. For a 150 car train with a minimum leakage, the brake pipe pressure at the first car drop 60 psi gauge of the brake charge. Brake cylinder pressure rises to about 48 psi gauge, roughly 55 seconds. At 150th car, the brake pipe pressure drops to 60, and the brake charge cylinder pressure rises to about 46 psi gauge, roughly 125 seconds. Since slack action propagates from 2 to 400 feet per second, the region of the generated slack run in during the braking along trains becomes apparent. Alright, then it shows a picture of the locomotive with the 22.6L automatic brake valve, air gauges, regular valve equalizer reservoir, main reserve 2 and 6 type, control valve, brake pipe, brake reservoir, cylinder relay, brake pipe, and it goes for the angle cocks, the hose couplings to the car. Also on the locomotive you have your brake rigging shoes and brake cylinders. Your car has a combined auxiliary emergency reservoir retaining valve with the ABD control valve with the brake pipe and with the truck mount bracket with the actuating brake cylinders. Another car combined auxiliary emergency reservoir retaining valve brake cylinder ABD with control valve automatic adjusting conventional braking. This shows another picture of a car for the auxiliary level retainer ABD control valve 3 slide with combined dirt collector cutout cock brake cylinder pipe. Brake branch pipe reduction retaining valve combined auxiliary and emergency reservoir brake adjuster for the current adjuster for the top rod. Brake beam, truck lever, connection, truck lever, handbrake, brake pipe, belt crank, angle cock, hose coupling, brake shoe. And that was figure 2.1, major elements of freight train air brake system. We'll go back to the page. 2.3, air brake system flow leakage, relationship with airflow leakage of the train brake system has several important effect for the brake testing operation responsible for the paper with the plane angle, makes several salient points regarding to the brake system leakage. Train air leakage is checked after making a 15 or 20 psi brake pipe reduction setting with a brake shoe. For the time of the brake pipe gauge drops over the 1 minute, however the measure only with the brake pipe leakage with the brakes relief for the air leakage with the control valve with the reservoir with the added give the total system leakage. Brake pipe leakage over 5 psi gauge, psi minimum gradients of over 15 psi cause an erratic brake response. Undesired application release of brakes may not respond. Leakage into the rear of the train has more significant effect with the train brake operation, therefore there is more benefit if corrected. Train length after the brake pipe reduction, time of the train average of the brake charge, brake cylinder pressure for the leakage, time of the speed over the brake pipe reduction, therefore with the leakage indicate induced gradient reduces the variable the pressure for the leakage speeds for the application time of the effect of the increase of the notability for the train length leakage up to 5 psi a minute produces shorter stops at 8 to 10 psi a minute. Brake pipe leakage stops distances adversely unaffected. The practical limit of satisfactory brake control is in leakage gradient situation with the flow of demand is a full charge condition less than 60 cubic feet per minute. In undated paper by the R.L. Wilson entitled The Factors Affecting the Air Brake Operation Effect with the Leakage of the Pressure Level of the Train Length of the Explorer of the determinative of the train charge time and the brake application of the pressure gradient with the later 1972 with the paper of the came off of the leakage of the gradient consideration train brake. Reference 4 Present Resolution Westinghouse Air Brake Division 150 car test under laboratory condition. In the test of the 80 psi gauge with the brake pipe pressure with the torque of the brake valve was used with the 50 feet of the brake pipe car. eventually disturbed the leakage. With the result of these tests were even determined with the gradient of the resulting airflow. 1, 2 with the brake pipe cylinder application time. 3 with the brake cylinder pressure. Build with uptime. 4 average train brake cylinder pressure. 5 with the simulated train stop at the distance. 6 with the release and recharge time. Of the result were applied with the various brake pipe lengths of the number of cars up to 7,500 feet or 150 cars with the corresponding between the brake valve with the airflow with eventually disturbed brake pipe leakage shown with the figure 2.2 based on the figure 2 for the Wilson paper, the current plot, carpet plot. Both train lengths of the solid lines of the pressure gradient dash line with are shown with a given the flow of the leakage concentrated the through of the front of the train would produce less pressure gradient with the leakage concentrated to the rear of the train created higher gradient, although with not specifically stated the leakage is assumed the measure by the AER method after 15 psi surface production, the brake pipe pressure and 30-60% 30 to 60 second time delay is noted with the higher leakage valve, the greater than flow rates were applied, and with the pressure gradient valves values cited by the Billing and Angle. However, laboratory rack test data reported Wilson was confirmed with a test conducted during the January 1978 with the Canadian Rail Operation Transcona Manitoba, cited in G. Smith's paper, October 1978, in reference 5. Wilson's paper 4 explores the brake cylinder pressure buildup at the time of the last car function of the brake pipe leakage for the train length for the test of the distinct with the minima, in particular with the longer train lengths as shown in figure table 2.1. Or table 2.1 shows the airflow method at 60 cubic feet, which comes across, and brake pipe pressure gradient 1510, 5 psi, 150 cars, 101 cars, 76, 51 cars, train length, and 50 cars. And this showed the 80 psi gauge of brake pipe pressure, 50 feet per brake pipe per car. The ABD and the 2.6 equipment eventually evenly distributed leakage, and that's airflow method and leakage of the psi over the minute. Corresponding airflow brake pipe leakage rate with the train length and pressure gradient. Table 2.1 shows the brake pipe cylinder pressure buildup with the verse of the train length of the brake pipe leakage. Number of cars 51 times 38. Seconds brake pipe leakage 12.3, 76 number of cars 76 times the 53 11.2. Brake pipe leakage psi minute 101 85 seconds time brake cylinder pressure buildup brake pipe leakage 7.3. 150 number of cars time in seconds 111 over the brake pipe pressure build brake pipe leakage 4.5. Alright, minimum brake pipe cylinder pressure for the build up at the time of the curved about the stream of the brake pipe pressure gradient of 5 to 7 the psi. Similar efforts for the round of the brake pipe application. The data was used to determine by the average train brake cylinder pressure for the calculate with the train stop at a distance for a full surface brake application. Calculate with the stop at a distance plot with the figure 2-3 with the first for the initial gradient flow with the leakage of the different train lengths loaded on 110 cars from the initial speed with the 50 miles per hour with the train safety viewpoint with noted curves are relatively flat and some variation in the brake pipe pressure for the gradient and leakage that can be tolerated. Other aspect for the brake pipe leakage with the pressure gradient are brake release time of the reservoir charge, recharge time of the bolt with the increase of the sharply with the increase of the gradient with the train length with the longer the recharge time and the increase of the time during the false gradient that exists within the train with which called the undesired brake release. During repeated brake application of the recharge time within 2 psi with the brake pipe pressure can take 15 to 30 minutes. The last car following the full surface reduction. We have stopping distance at feet time 1,000, so we have 4,000, 5,000, 6,000. Right around 4,000, you have the leak pipe and PSI minimum at 51 cars. And 5,000 feet, you have 101 cars at airflow method cubic feet per minute. And 150, 40, 50, and 60, 70 train lengths at 6,000 feet. And that's brake pipe pressure gradients, 80 psi gauge brake pipe pressure, 50 miles per hour initial speed load of 100 ton cars. 7% of the net design braking ratio, full surface 25 psi reduction, ABD and 266 equipment. 2.4 airflow test methods for the 1978 with this paper by Smith and Wickham addressed the airflow alternative with the pressure drop of the leakage depth of the several pertinent observation within these papers. Pressure maintaining valve of the 26L with the locomotive braking equipment equivalent appear with the key to development of the brake pipe pressure for the with the locomotive engineer sets to the avoiding with the increase of the brake cylinder pressure for the braking for the brake pipe pressure fails to the due to the leakage of the consequently with the periodic relief of the reapplication of the train brakes. Brake pipe leakage allowed cannot simply be raised to save with the 8 psi a minute will take advantage of the pressure maintained with the feature of the continuous quick service valve with the stability level of a little over 5 psi a minute with accelerated application of valves about 7 psi a minute during the leakage shift of the true with the leakage 8 psi a minute would cause some value to operate with a give of the false leak with perhaps 11 psi a minute. Brake pipe pressure drops on the test only when the brake pipe leakage after 15 psi with the production when the airflow test felt totally system leakage at the full brake pipe pressure. Training with not maintaining the valve that happen to meet the 5 psi minimum leakage controllability limit while the trains maintaining brake valves can utilize 60 cubic feet a minute with the flow of the controllability limit. For the most trained, the airflow method would normally take longer than the brake pipe leakage method, but since the 15 psi with a gradient value, usually not finally stabilized value for the longer trains where 15 psi gradient is deciding factor, the airflow method would save the break-even point with about 147-50-foot cars. Airflow method can allow the trains to be put into service which otherwise may be rejected for no good reason. Computer prediction with the effect of the larger distribution given in the 1979 paper with the shoe with the reference 7, the results show with the brake pipe pressure gradient sensitive to the location leakage and train with increase of leakage to moves reward. Leakage less than 10 psi a minute with a brake pipe flow with the nonsense for the distribution of the leakage. Both of the reference 6 and 7 site with the airflow levels less. Reference 4 with the corroborating field test of the reference 5 for the given leakage rate with the pressure gradient. Since of the 1981 with the airflow method of the Canadian Railway Operation Canadian Transport Commission with the reference 8 with the cover of the background airflow method test railway experience training the operation economic factor of the one section 217 provided with a direct comparison with the leakage airflow method test. Method of the testing train air brakes of the comparison with the given the figure with the 2-4 with the contained with the basically with the same and important points cited with the above with the reference and economic benefits identified with the Canadian Railway 3 years following the implementation of the airflow method of the 15.4% increased winter train load with the result of the crew wage savings diesel of the unit with the caboose mile saving identified with the annual operation savings of the exceed $6 million Canadian. An additional savings were projected but not qualified for the motive power with the caboose acquisition revenue freight car requirements plant capacity. The airflow method cited in the 1981 paper of blame with Angle and the Peterson reference 9 in the section titled the determination of satisfactory train brake condition. 2 figures in the paper of relation for the brake pipe gradient with the airflow leakage train with the brake pipe length with the bowl with the leakage airflow method does not repeat with the figure 2.5 with the flow versus leak of the value with the closely corresponding on the side with the Wilson 4 showing figure 2.2 with the author shape with the valve dove with the 60 cubic feet a minute limit have been subject with the service trial with the airflow method that has been used over the 3-year period for over 1 million miles initially intermediate with the terminal train testing in Canadian railways. We missed 2.4 which the leakage of airflow method of testing qualifying training air breakage. You have the brake pipe leakage and your airflow method leakage, and it's a little bit small to read, so we're going to continue. Double presentation operation experience airflow method that has been reached for the year with the Rail Fuel Operation Officer Association edition with the Canadian Railroad 5 and 10. The CP Rail experience gained with the Burlington Northern and South line of the railroads that were presented in the newspaper. The operation experience included reports by locomotive engineers, sampled of the train brake with the test of both of the method of the direct comparison, no problem with the train handling. Train safety were found and attributed to the airflow method. 2.5 recent brake system study with the Federal Road Administration sponsorship of the recent freight train with the brake system studies, safety study with the aim to develop the understanding of the brake system operation with the train brake, the dynamic response. One each step with the reference 13 with the draft the 2 items of the moment is others for the brake system, the dynamic performance of the type of the airflow method. B, to study the feasibility of acquiring locomotive equipment with the brake pipe flow indicator for the name of the entry for the measure for the train airflow line, National Train Safety Board Safety Recommendation R 7985, January 10th, 1980. B, can a train linkage increase for the initial terminal brake test over the present 5 psi per minute safety? And show the leakage gradient versus the train length of the brake pipe pressure leakage, brake gradient level in bar, brake pipe gradient PSI, 15 PSI gradient related, 5 PSI minimum leakage constraint in the rear, 5 PSI minimum leakage eventually distributed, brake pipe linkages 2,500, 5,000, 7,500, and 10,000 brake pipe length. Then you have an airflow gradient leakage the limits versus train line. So for the airflow method, 0 to 110 in 10 minutes increments, 6 cubic feet an airflow minute, 5 psi gradient, 5 psi minimum leakage AAR method, 2.5 comparison leakage airflow limited criteria. In this study, the pressure gradient leakage train with the top of the distance model with the developed conclusion reached for the essential of the chain of the previous reference cited increased leakage rate possible only because of the widespread application for the pressure maintaining valve of the airflow meters on the locomotive. Leakage rate test is measure controllability of the brake system when assumed the system is not equipped with the pressure maintaining equipment. A, the relaxed leakage rate test of the 7 psi minute would not compress the comparability with the pressure maintaining equipment, but some valves would operate increases in leakage for the nullifying with the test. Airflow would test for the system leakage with wherever the current method of the test only with the brake pipe leakage with typically 70% of the total system leakage. A flow rate meter allowed for the continuous monitoring of all of the brake system, and the airflow meter is more straightforward with less room for error. A simple formula developed with the pressure drop name of the leakage at various time and the exponential of the decay of the pressure of the time and the constant of the variable forming the variable with an inverse square root with the absolute pressure over the fixed for the leakage for the warming of the brake pipe, the air, faster of the pressure drop at the time when the constant may vary from 50 to 20% of the typical winter to summer temperatures. However, the leakage generally increase with the colder temperatures, pretending to the offset with this change in the time constant. Other efforts to over the mathematical model with the train air brake system has reported in reference 14 through 18 of the most recent 1988 publication Adal Abdul Ahmed Limbert Chapman, reference 18, entitled for the effect of the leakage of the railroad brake pipe, study with the state of the behavior to discuss the mathematical model, pneumatic transmission lines for the brake pipe with leakage for the model utilized with one dimension with the continuing with the momentum equations, using finite difference techniques for solutions for the conclusion of the study included the following. Pressure gradient is larger than the leakage moved over the rear of the small the leakage of less than 2%. Leakage location has little effect with flow rate with larger, greater than 8%, but there is increased flow of the leakage moved forward. Leakage side with a great effect for the pressure distribution, larger side with a less, greater than 8%, but it does not have an effect for the inlet flow since pipe friction tends to control the flow. The fitness of the brake pipe can be determined based on the pressure gradient and flow alone. Both must be used. The recent study of the ARU, the undesired emergency study of the reference 19 was reviewed. Context of the airflow method of the train brake qualification of the none, but the conclusion study of the undesired emergency application of the train brakes indicate that the airflow method would in any way jeopardize brake system integrity with the train safety. 3. Evaluation of the airflow method. We're going to cut our tape first right there.